So this is our problem. It's 17.45 out of the suggested homework problems to do. So it says uniform rods A, B, and BC are of mass 3 kilograms and 8 kilograms, and then point C, which is like a little collar type thing. This is C, has a mass of 4 kilograms. Knowing that at the instant shown, which I just called t equal to 0, we're not going to use that anymore. I'm just, just my shorthand of doing it. But knowing at this instant, the velocity of C is 0.9 in the J, negative J, that is. Find the velocity of B after rod AB has rotated 90 degrees. So, looking at this problem, you might not know where to start, but there are some clues. So specifically, we're asked to find the velocity of B after something happens, right? So it tells you and shows a picture of the system before something happened, and then it tells you to find some information about the system after another event has happened, right? So this is precisely where we use work energy. Like the kinetic energy at point 1 plus potential energy at point 1 equals the kinetic energy at point 2 plus the potential energy at point 2. So more specifically, this is state 1, like this is our system, and state 1. And then state 2 is find velocity of B after rod AB. This rod right here has rotated 90 degrees, right? So now this is our system. This is state 2. And we're trying to find the velocity of this point right here once it's in this state, right? So you have two states. This is, textbook definition of when to use work energy. So kinetic energy at point 1 plus the potential energy at point 1 plus the work from 1 to 2 equals the kinetic energy of 2 plus the potential energy of 2. We all recognize that equation? Yeah? Okay. So, if you recall, kinetic energy in general is 1/2 mass times velocity squared. That's the translational motion part. But, what you've been tortured with in dynamics is now the rotational stuff. So it's now I omega squared. I think this is also 1/2. Yes. Yeah, so this is kinetic energy in general now. So you got the translational component, just like motion like this, like what this marker's doing right now. And then you've got, the angular part. So kinetic energy is both of that. So if, this is kinetic energy in general, potential energy really isn't anything crazy. You have potential energy due to like springs and stuff. There's no springs here. It's just gravity. So mass times gravity times height, that's potential energy. And we are not told about any applied forces, and we're not told about any distances in terms of an applied force. We're not told about friction, and friction being applied through a distance. So this goes to 0 just for this problem. Because work is force applied through a distance. We're not told that there's any force, and we're not given like a coefficient of friction. So that's a hint right there that, this term's gonna go away. Obviously in real life that would never happen, but we're assuming no friction, there's no applied forces, that goes to 0. So the base equation we are trying to solve, kinetic energy of 1 plus potential energy at 1 equals kinetic energy at 2 plus potential energy at point 2. So this is our simplified base equation. And how I'm going to solve this is I know the velocity of B in this state 2 is what I'm trying to solve for, right? I know that's in this term, kinetic energy of 2. The term that I'm trying to solve for is in this term right here, but I can't expand this equation because it would literally be so long, because this right here is for like one thing. This is like, if you want to be specific, kinetic energy of point A, mass of A, velocity of A, you know, so you'd have to do this for A, B, C. The equation would get so long. So I literally can't write it in one thing. So how I'm going to do this instead is, like, I'm going to solve for the kinetic energy of 1 and then actually get like a number for it and then stick it into here and then get the potential energy of 1, stick it in, potential energy of 2, stick it in, and then, yeah, that's how I'm going to do this. Versus, you know, like usually I show the entire equation with all the variables, but I can't do it here. It's just, the equations are too big. So, everyone cool if I erase this? Yeah. Okay, so we know what we're trying to solve for, right? We're going to find kinetic energy and potential energies and then use that to solve for what the value of kinetic energy should be. And then we're going to use that number and then expand the kinetic energy of point 2, and that's how I'm going to solve it, right? So we have to start somewhere. Kinetic energy at point 1. So this is state 1, and now we need to find all the kinetic energies associated with it. So we have So now it's becoming pretty apparent why I can't fit this all onto one side. So this is all literally just for the kinetic energy of 1, right? So the mass of AB times the velocity of rod AB. So again, that's rod AB. Then plus the rotational part of AB. So the moment of inertia times its angular velocity. Same exact thing for BC, mass of BC, velocity of BC, then the rotational part. And then for C is just this collar, and it's like constrained in this little rod right here, so it's not rotating at all. So C is just translational part. Does that make sense for everyone? So you might have been confused to, like, why didn't I do kinetic energy of 1 equals 1/2 mass of A times velocity of A squared? Because although like this is an okay thing, what I'm trying to say is like when we're trying to find the velocity. So if this is A and this is B, I'm going to quantify this entire rod by calling this right here like X, and then, you know, it's center of mass. You use its center of mass instead, right? So that's how I'm going to solve it. Okay, so, and doing that, like this term right here, mass of A, that kind of doesn't really mean anything. Like, we're given the mass of the rod itself, not of point A, so it doesn't really make sense. So that's why mass of AB, velocity of AB. So, mass of AB, we are given that in the problem. Moment of inertia, we don't have it, but it's easy to get. It's not important. Angular velocity of AB, we don't have. Mass of BC, we have that. Velocity of BC, we don't have that, but I'm going to go a little bit more into that. We can get this pretty easily. Angular velocity of BC, don't have that. We have the mass of C, and we have the velocity of C. So, now what? And just one more thing, I'm putting these ones right here just to emphasize that we are in state 1 of the problem, because I'm going to have to do this exact same thing for state 2. So if you wanted to be really technical, it would be like mass of C. Actually, that's a bad example because the mass of C does not change. Velocity of C in state 1, right? But this is just an easier way of writing it. Okay. So the velocity parts, velocity of AB, this is exactly what I was talking about. So if we have like, this is A, this is B, I'm going to call this X. Now I'm saying velocity of AB equals the velocity of X. Because we're talking about this rod with translational motion, right? So this entire rod, this is point A, this is point B. If it's just translating, then the center of mass of this marker has the same exact velocity like as the entire rod translating. That's not true for rotation, because as we've learned, rotational velocity depends on the radius and stuff like that. But translation, the ends of this marker are going at the exact same speed as its center of mass with translation, right? So that's how I solved this. So now I'm going to call velocity of AB velocity of X. In the same exact way, I'm going to call the velocity of BC the velocity of Y. And I'll label that. So I'm calling this Y and I'm calling this X. So then Y, X. And everything else can stay because angular velocity of AB, that makes sense. You can answer that, so does BC. And then velocity of C, that is okay too because it's not rotating, it's constrained in a little pole thing. So, okay. So, don't know that, don't know that. There's a lot we don't know here. So, I'm going to start with the velocity of X, again, at point 1. So, what do we know? We know that if this is B, this is X, this is A, then the velocity of X equals the velocity of A plus okay. So here's an equation for it, for the velocity of X. So the velocity of A is a pin, right? So it's 0. So the velocity of X at state 1 equals angular velocity of AB crossed with the position vector X with respect to A. So 2x from A, so we're going negative in the I. We're given this right here, but it's half of it, right? So this equals Any questions there? So evaluating cross product. I don't have the angular velocity of AB yet, but it's okay. Okay, so this is what? K prime size, J. Okay. We have the velocity of x1 in terms of omega AB. So just to give you a hint of where I'm going with this, or in general, I can substitute this term for this now, right? And I've kind of eliminated an unknown because this was unknown, but so is this. But I'm substituting this in terms of this variable. So I just eliminated an unknown by doing that, right? Everyone sees that? So I'm not going to do it yet, but that's, that's the process that I'm going to be doing here. All right, velocity of B at point 1. We figured out all we can about this. So now looking at the other points on here, the velocity of B equals velocity of A plus omega AB cross RB with respect to A. Velocity of A is 0 again. Velocity of B is then AB. So angular velocity of rod AB crossed with the position vector 2b from A. That's negative 0.15 meters in the I direction. Then you do the cross product again, and you get this. Okay. So now I have, what's up?
What's the vector, or does it not have a vector?
Oh, it does, yeah. Also in the J direction. J. So. Okay. I still didn't find any numbers, but now I know that I know terms. I'm eliminating unknowns here. So, all right. Is everyone good if I erase this? So it seems like if I figure out the angular velocity of AB, I would be able to figure out a lot more stuff because the past two things I've done, I've gotten it simplified all the way down until it's just the angular velocity of AB times some number, right? So if I find the angular velocity of AB, I'll be able to figure out a lot of stuff here. So now I'm going to look at rod BC, and the motivation for that is rod BC at point 1, because I know the velocity of C in this state. So I can do stuff with that to then figure out the velocity of AB. So from that rod, we have velocity of B equals velocity of C equals. So velocity of C is given, angular velocity of BC. I don't have it yet, but it's good that it's showing up now because I'm going to need to get it at some point, right? So then this is just the position vector. I don't have time to go through all this stuff because this equation this problem is ginormous. So anyways, so what I'm going to do here is I'm going to say velocity of B, I found it in terms of this, right? So this is velocity of v. It equals 0.9 in the j plus bc. So after doing the cross product here, after doing the cross product here and then expanding things, this is what I get. Negative 0.15 times the angular velocity of AB in the j direction, and that's important, equals negative 0.9 in the j direction plus negative 0.36 times the angular velocity of BC in the I direction minus this. But the important thing here is, if I split this into I and j components, there is nothing in the I direction on this side, right? Because the velocity of B was only in j. But we see right here, the angular velocity of BC, this term is in the I direction. So 0 in the I equals negative 0.36 BC, also in the I direction. From this, you get rod BC is 0, has no angular acceleration, or velocity rather. Does that make sense, everyone?
Only in the I, right? Or in general?
So the angular velocity is in the k direction, right? So now we know this term is 0. So going back to here, this term is 0, this whole term, right? Okay, so that's 0. And now, because that's 0, is everyone good if I erase this? Looking in the j direction of that same equation, negative 0.15 AB in the j equals just negative 0.9 in the j. Because, you know, this is 0, that's 0, they just go to 0. So now we can find the angular velocity of AB. So, what does that equal? Equals 6. 6 in the k. And again, that's at 0.1. So now we have that. Any questions there? So if you recall, I had velocity of b and velocity of x in terms of the angular velocity of AB. So now that's my next step. I'm going to solve for all those. And then we're almost done with 1/4 of this problem. Yeah, these things, dynamics is quite the class, but okay. Now we have that. Everyone good if I erase this? Okay, we said velocity of B at 0.1 was equal to negative 0.15 omega AB, and that was in the j direction. So now we can solve that directly. So this is equal to just the computation, it's just this. Velocity of B at 0.1 is negative 0.9 in the j direction. So velocity of x1, we had it earlier, it was just negative 0.15, but over 2 times AB in the j. So velocity of x at 1 is so doing the computation, that's that. Okay, what can we say we know at this point? Doing this part all over again. because we figured out a lot here. So we know velocity of x. We can get this. I'm actually not even going to compute it. I'm just going to give the number because it's so trivial. Angular velocity of AB, we found that. BC, we still have to do something about the velocity of point y because we don't have that yet. That whole term went to 0, and we are given this stuff. So we're almost done with this portion of the problem, kinetic energy at point 1. Last step is velocity of y at point 1. So is everyone good if I erase? Now, the velocity of y. So, looking right here at this rod, the velocity of y equals the velocity of b plus the angular acceleration of bc cross ry with respect to b. But we proved that the angular velocity of bc is 0. That whole term goes away. Velocity of y equals the velocity of b. And we just found the velocity of b was, what was it? It's negative 0.9 in the j. Any questions? Okay. So, now we know that. That's our last thing here. Everything is known now for the kinetic energy of point 1. So it's just computation at this point, and I don't have time to go through all of it. But trust me, at this point, you have all the numbers. Well, except for this, the moment of inertia. But like I said, it's just one of those things you're just going to look up on an equation sheet. You're never going to have to really solve for it. It's really not that hard. Just looking at it and plugging in the numbers that you're given. It depends on the length of your rod and the geometry, and it tells you it's a uniform rod. So you literally just look at the equation sheet and stuff like that. So. Kinetic energy at point 1 of the entire system is 5.265 joules. So, now in my equation I started with, I know that now. And just to reiterate one more time, I'm trying to find the velocity of b at state 2, and I know that term is in the kinetic energy term. So what I'm doing, I just solved kinetic energy of 1, now I'm going to do potential energy of 1, and then potential energy of 2, and then solve. That's the process here. So is everyone good if I erase this side? Luckily, the potential energies are a lot easier. The kinetic energies are the challenging ones. So, potential energy at point 1. When we're doing potential energy, we have to make a claim about where the 0 point of potential energy is. And you can really do it anywhere on your system, right? But there are points where it makes way more sense to do it. So I'm going to say 0 is right here in terms of y, because potential energy, mass times gravity times height. I'm saying y of 0 is right here. And the good thing about that, the potential energy of AB is 0 now, right? So that's why I'm doing that. So potential energy of 1 equals, let's see, mass of AB times gravity times height AB, I just said that entire term was 0. And it's also equal mass of BC times gravity times height BC. And the way we quantify the height of BC, it's the height of Y, its center of mass. Are there any questions there? So instead of the height of BC, because that doesn't really make sense because it's a rod, it's not like a point, you quantify the height of BC with its center of mass, which is Y. Okay? So then the last term is the collar C. Mass of C times gravity times the height of C. So this one goes a lot easier. So you have mass of B, you obviously have gravity. Height of Y, you have to do a little bit of work for it, but you have it, you can get it. Mass of C, you're given, gravity, you're given, and the height of C, you're given as well from the problem statement, or the problem system, right? So, is anyone confused on how I know that I already have all of these numbers? No? Okay. So, the one thing that may be confusing, height of Y is going to be, and height of C, they're both going to be negative because they're below the 0 line. That's the only thing. They're not positive numbers. So the entire potential energy of my system at point 1, negative 0.2528 joules. Any questions? Just for your computation, if you guys want to do it, it's Y is negative 0.36 over 2, and H of C would be negative 0.36. That's all it is. So, and then the masses you're given. So, all right. So now this term, I'm going to replace it with the number negative 28.25. All right. Is everyone good if I erase this? Potential energy at 2. So this entire class so far, we've been looking at this system. Now we're at state 2, where the bar has rotated 90 degrees, so now our system's like this. And my 0 point is still right here. So now trying to solve for that. So potential energy of 2 is equal to the potential energy of AB at 2 plus potential energy BC at 2 plus potential energy C at 2. And now because the system's moved, the entire thing has potential energy, whereas last time I was able to cancel out this, but now I can't do that. So, but it's really not much more work. So potential energy of 2 equals mass of AB times gravity times height of AB. But remember how I'm quantifying the height of AB is by its center of mass. So height of point X. Then same thing for BC. So mass of BC times gravity times height of Y plus mass of C times gravity times the height of C. Any questions? So go through this, have that, I can get this, I can get the, or I have that, gravity you have, I can get this, I can get the, or have that, and I can get this. So we know after, a little bit of computation, I will finally have this part, right? So the one thing I am going to do here is, so height of x is negative 0.15 over 2, but the height of y, and I didn't see this when I was doing it, it's not this number. You have to use the Pythagorean theorem because like when this moves, you have to find the length of the hypotenuse, right? So you might be, and when you do the computation with this number, it's really not that much different, but the height of y is square root of 0.36 squared plus 0.15, right? And then this whole thing is negative times negative 1. So that's the height of y, right? And then the height of c is just, height of c is, is this how you get this? Hold on. That whole thing divided by 2. I got a little ahead of myself. That was the height of c that I was doing. So the height of y is, this length. So that, describes like this portion of it, but then this is halfway up it. So divide this whole portion by 2. Okay, but it's just a little bit confusing if you can't, really see it from the system, but at this point, it really just is computation. So if anyone's confused about, the height of it, just ask me after. In the same way, you can find the height of c. So from the Pythagorean theorem, and just adding and stuff, and it ends up being potential energy of 2 is negative 50.47 joules. Are there any questions?
Actually, I do. So this just goes back to the kinetic energy of 1. Even though we know that the velocities are negative, do we still compute that back into the equation that we have, like especially the direction of them? Like, do we have to include them as negative values, or do we use them as positive?
Oh, because you're squaring it. Is that what your question's getting? So when you square it, it doesn't matter that it's negative.
Okay.
Right, so. Okay. So now we have this. Negative 50.47 joules. So now I can find the entire kinetic energy of 0.2, but I know that what I'm asked for is locked up inside of this term, because kinetic energy is not just like one thing. It equals 1/2 mass times velocity squared, all that stuff. But how I got this number, the first part I did, I'm going to have to do that all over again, but this time I'll know what it equals. I'll know what it's supposed to equal, and that's how I solve. So that's the last step. But as you saw from the first one, the first kinetic energy, the kinetic energy ones take quite a lot of time. So, all right, kinetic energy at 0.2 equals, for instance, like this number right here. I know this now from that side, but it equals 1/2 mass AB times the velocity of x squared plus 1/2. Okay, so I have that. I do not have the velocity of x. I had it at point 1, but you can't assume it's the same. You can get that. I don't have that anymore. Don't have that anymore. Don't have that anymore. And I don't have that anymore either. We started with velocity of c at point 1. I don't know what it is at point 2. So there's a lot of unknowns here. But we knew this in the first one, but we didn't know what this side was. That's how it evens out. I can still solve this because I know what this entire term itself is supposed to equal, right? So, okay. All right. Velocity of x at point 2. So looking here, velocity of x is going to be equal to the velocity of a plus velocity of x equals velocity of a plus the angular acceleration crossed with the position vector. Velocity of a is still 0, so velocity of x equals ab crossed with this is the position vector. Velocity of x equals 0.15 over 2 times this. Any questions? So where I'm going with this, I'm going to solve for everything in terms of variables and then use substitution so that this way, this problem only has one unknown. And I'm going to design it that way so that the one unknown is the velocity of b at point 2, because that's what I'm trying to solve for in the first place. So it's not so apparent here, but with this next step, it'll be pretty clear what I'm doing. What's up?
I had, or what's the?
Yeah, k cross j. Yep, I. Yep, that is important, so thank you. K, velocity of b. Looking at point B, velocity of b is velocity of a velocity of a is 0 again. Velocity of b, just by doing this. Any questions?
How'd you get negative 0.15 over 2 to negative 0.15?
Oh yeah, that typo. Yep. Yep. Yeah, because b is the entire length of this, not over 2.
Okay.
Yeah. So good catch there. So that's the velocity of b. See, I'm solving everything in terms of variables, and that way I'm going to design it so that I can substitute all of these unknowns in terms of velocity of b. So now, I don't have time to prove that. I don't have time to prove this, but the velocity of c at point 2 is 0, and it's because of the instantaneous center of rotation stuff. So if you look at the velocity vectors of like x, b, and y, you'll see that when you draw like the instantaneous center of rotation, they all intersect at c. So the velocity of c is 0. I can prove it after if anyone's curious, but I don't have time to go through it. So this whole term goes to 0. So now velocity of y at point 2 is equal to velocity of y equals the velocity of c plus bc r v with respect to c. That's 0. Velocity of y equals You just got to get the position vector, but you're given everything there. Negative 0.36 over 2 times dc. That's in the I direction. So that's the velocity of y. Questions? Okay. So. Everyone good if I erase this? There's only 1 minute left, so there's still quite a lot of steps here, honestly. So you guys are free to go. I'll keep going if anyone wants to stay, but
Okay, I guess shit then. Oh, sorry.
you're good. You're good. Yeah, I mean, I even skipped a bunch of steps, and you see how crazy this equation got, this problem. What's up?
I just had a question about, you know how where you mark 0?
Yeah.
Can you mark 0 on the y-axis in line with the whole system or no?
You mean like this way?
Yeah.
No. Because, you know, like this, like if I say this is x and this is y, this line right here would be like y equal to 2, right? So if you draw a line this way, that's x. So in height is, y direction.
Right. Okay.
So yeah, has to be that way. What's up?
The 0 would always be at the pin, right?
You can put it anywhere you want to, but I put it there because in state 1, when you put it there, you can cancel out the potential energy associated with rod AB because it's at the 0 line. So. So thank you for listening. If you guys want to before you leave, just come over and look at my solution sheet if you want to. If you want to see how to solve it, but there is still quite a few amount of steps. But the process, I solved for everything in terms of variables, and then I'm going to design it so that I can say, for instance, I'll give an example. I know that the velocity of x at 2 is equal to 0.15 over 2. I found this earlier and I proved it, right? But I then found that I didn't prove this one yet because I ran out of time, but I found that angular velocity AB equals this term. I can substitute that in, right? So then after doing that, this would equal velocity of x2 would be velocity of b2 divided by 2. So now that I have that, everywhere that I see velocity of x, I stick in velocity of b over 2. And you do that entire process for these, for all the unknown variables. And you can, because you can solve it all in terms of velocity of b. But as you see, there are still a couple variables I didn't get to, but that's the process. So I'll post my solution sheet online, but yeah.